Hi, and welcome to my presentation on Omni. We present a method for volumetric sensing and actuation of passive magnets, especially for haptic feedback systems. Virtual and augmented reality are gaining more momentum due to their promise for immersive experiences. However, to increase the immersion into a carefully crafted artificial world, it is necessary to also support the sense of touch. A lot of prior work exists on this, ranging from complex mechanical designs to vibro-tactile stimuli to larger electromagnetic surfaces. The main challenge of closely related work, such as normal touch by Benko and colleagues and butterfly haptics by Bergman and colleagues, is that they require external tracking or are desk-sized. This gives rise to the question on how we can leverage electromagnetism to simultaneously exert haptic feedback as well as track an input device. To this end, we have three contributions in our paper. First of all, we have a hardware contribution. Secondly, we suggest a method of precision reconstruction. And finally, we actuate at the same time. Let's first discuss the hardware. Our system consists of a permanent magnet embedded in a tool. The main actuator consists of a spherical electromagnet. This is constructed around an iron core and consists out of 3 orthogonal coils. Below that is a PCB with 8 3-axis Hall sensors, which enable tracking. The whole system is cooled by a single fan. Now that we have an overview of the hardware, let's dive into details on the tracking. To understand our method, let's start with the inputs. The first step is to measure a Hall sensor. This provides you with a magnetic field at a certain location. This magnetic field is influenced by a permanent magnet in a tool. However, it is possible to approximate this influence with the dipole-dipole model, denoted in blue. This influence depends on the pen position relatively to the sensor. We can use a similar model to approximate the influence of the spherical electromagnet. So now our Hall sensor measures the tool, the actuator and noise. The measurement can be approximated by the sum of the models, since the magnetic field forms a superposition. By minimizing the square difference between our model and our measurement, we can estimate the pen position P, which is a solution to this problem. Here you can see the tracking as observed through a mixed reality headset. Since the method uses gradient descent under real-time optimization, it takes approximately 50 milliseconds to converge. We now have an actuator that can track our tool, but how do we actually provide force? The force in 3 directions can be changed by altering the current, thereby delivering forces that are perceived in different directions and strengths. During experiment, we have measured forces up to 2 newtons for 30 seconds. Lower forces can be sustained indefinitely. This is enough to launch the pen or lift an apple. With ferromagnetic fluid, we show that we can change the direction of the magnetic field. And here we use a permanent magnet found in our tool to illustrate that we can supply both tangential as well as radial forces. Let's take a look at how accurate we can track. For this we use the 10 camera OptiTrack. We measure the tracking with and without actuating. Without actuating, we found that we had a tracking error of 4.9 mm in Euclidean distance. This increases to 6.9 mm when we actuate. However, overall, the error per axis stays well below 5 mm. Let's see what kind of use cases our system enables. Here, a designer is extruding material from a shape. An attractive force is felt during extrusion. Our system can also be used to explore non-rigid bodies. Here, a tangential force is felt whenever the dragon is touched. Finally, it can be used in gaming, here in a joystick-like fashion. A heavy, attractive force is felt when the user bumps into the wall. To summarize, we made 3 distinct contributions in our paper. We have novel hardware, a tracking algorithm, and actuation at the same time. Omni's capabilities allow spatial interaction systems to integrate 3D tracking and actuation of untethered free-range tools, simply by embedding a small permanent magnet. Thank you.